In this problem, we have a rocket that takes off vertically with no initial velocity but with a constant upward acceleration. After some amount of time, the engines fail completely, so the only force left on the rocket is now just going to be the regular pull of gravity. So what we're going to go through and do is try and find the maximum height that the rocket will reach above the launch pad. So this is a two-part problem. If I go through and think about what's going on in this problem, I have my initial, I can't draw a rocket, my initial rocket with its initial velocity of 0 is experiencing an acceleration, which I'm going to mark as a sub 1 initially. So it has an initial acceleration. And so this rocket is going to keep moving upwards until that point where the acceleration stops, where the engines cut off and this constant upward acceleration disappears. It's going to have some velocity at this point though, so but we don't know what that is. So I'm going to mark this as velocity stop. I don't know what it is, but it has an upward velocity. I do know that that velocity, and I'll mark this as still moving upward here at V sub S, S for stop. But now at this sort of point where the engine stopped, the acceleration changes from pointing upwards to pointing downwards. And now we're in free fall. But it's still going to move upwards a little bit more before we get to the point where the rocket itself, I should stop drawing little engines at the end, where the rocket itself now has no velocity. So we're going to call this velocity peak. And at that point, we know the velocity is going to be 0. And that is the height that we are trying to figure out. So all the way from its initial launch point, the delta y is what we're going through to try and figure out. So let's go through and sort of collect together our knowns and our unknowns so that we can go through and look at how to solve this problem. But for the most part, we're going to divide it into part 1 and part 2. And the reason we're going to divide it into those two parts is that those two parts each have a different acceleration. And based on the problem, it's an instantaneous change in acceleration. So I can treat part 1 as constant acceleration and I can treat part 2 as constant acceleration. They just have two different accelerations. So let's start with our what do we knows, our knowns. So I know that that initial velocity is 0. And let's go ahead and say that that initial position is also going to be 0. It tells me that my acceleration during all of part 1 is 2.25 meters per second squared. And the elapsed time that it's in part 1 is 15.4 seconds. So my engines burn for 15.4 seconds before it stops. And so I could break this out if I wanted to and say that my initial time is 0 and T stop is 15.4, and that gives me the same elapsed time that I wrote there. Then if I go through and think about what's going on in part 2, I'll just draw a little line here. I know in part 2 my acceleration changes. So now it's no longer going to be positive, it's going to be negative g. So negative 9.8 meters per second squared. I know that during part 2 it's going to eventually get to this peak velocity, and I know that that peak velocity is 0. And I want to try and find out what that total distance is, and I'm going to need to find out some things in the meantime. So I'm going to write over here my unknowns, and I'm going to think about these as part of each of their parts. So if I look at all my knowns at the top above this line, here, these are all the ones for part 1, and these are the ones for part 2. So if I look at part 1, I have an elapsed time, I have an acceleration, I have an initial velocity, but I don't know what the velocity it is when it stops. And I have an initial position, but I don't know what the position is when it stops. So those are my unknowns for part 1. For part 2, my unknown or unknowns would be actually both of the ones I just started with. The velocity at which part 2 starts happens to be the velocity sub-stop, same with the position. So the other things that I don't know are the distance it travels in that part 2, that elapsed distance, as well as the time. But I think I can go through and figure out what that is without the time. So I'm going to call y peak. I'm going to say that's another one of my unknowns. And so if this is y equals 0, this point right here is y sub stop. Then this position up here would be y sub peak, just so that we make sure that we fully understand what it is we're looking for. So that means that the delta y that I want to figure out is going to be y sub peak minus y sub 0. And I already know what y sub 0 is. So this is the real thing that I need to try and figure out in the end results of all of this. So like I said, we've divided this into 2 parts. Part 1 is when those rocket engines are working. So we need to find that velocity when the engines stop and the height of the rocket when the engines stop. So to start, we'll start with v sub stop. So I'm going to use the equation that involves final velocity equal to initial velocity plus acceleration times elapsed time. So if I plug in for my particular problem, this is going to be v sub stop equals the initial velocity plus my acceleration sub 1 and delta t stop. So I know that that initial velocity is 0, so I can get rid of that. And I know what my acceleration is. And I know what my elapsed time is. So if I plug all of that in, I'm going to find this velocity is going to be 34.65 meters per second. So I'll mark that over here. So next I need to go through and figure out what my elapsed distance is at this point in time. So to do that, I'm going to use the kinematic equation that involves final position is equal to your initial position plus your initial velocity times your elapsed time plus 1/2 acceleration times elapsed time squared. So now if I plug this in using the notation we're using for this problem, this is going to be y sub stop. This is the initial position. This is my initial velocity times delta t stop plus 1/2 a1 delta t stop squared. Now that initial position is 0 and my initial velocity is also 0. So that leaves me with 1/2 a1 delta t stop squared. I can plug in those numbers. You plug that into your calculator and you'll find that that distance is 266.8 meters. So we'll mark this up here in the corner too so we can keep track of the things that we found. So these are now new knowns that we have calculated. Now, we're ready to move on to part 2. So this is when the engines stop working. And so what was our final velocity and final position for part 1 are now our initial velocity and initial position for part 2. So we're going to use another equation because what we want to try and figure out is a distance. We don't have a time and we actually don't need to go through and calculate a time. So I can use the kinematic equation that involves the final velocity squared equal to the initial velocity squared plus 2 times the acceleration times the change in position. So we're going to plug this in for our notation here. So this is the peak velocity squared is equal to the stop velocity squared plus 2 times the acceleration in part 2, which we know is negative g, but we'll plug that in a moment. And then delta y is going to be y sub peak minus y sub stop, because we're only focusing on part 2, that's not y sub 0. So important to keep in mind what your range happens to be. Now this peak velocity is 0, so we'll lose that. And we can go through and start to rewrite things a little bit. So v sub stop squared is going to be equal to negative 2 times the acceleration in part 2 times the difference in distance in part 2. We're going to start to do a little bit of algebra because, again, my goal here is to try and find y peak. Notice I'm not plugging any numbers in yet other than things that I know have to be 0. So y peak is then going to be equal to y stop minus the velocity when the engine stop divided by 2a2. So now I'm at the point where I could go through and plug some things in. And again, I could have, if I wanted to, gone through and realized that that this negative sign would disappear because a2 is negative g, and so these would become positive. I could have done that already. That's fine. Up to you whether you wanted to do that sooner or later. But now we can plug in the actual numbers. So the vertical position the rocket is at when the engine stopped, we calculated before from part 1, was 266.8 meters. We calculated its velocity when it stopped as 34.65 meters. And then we know what the free fall acceleration happens to be. So if you go through and plug all of that into your calculators, you'll find that the peak height is 328 meters, and that is as measured from its launch point, because that is how we initially defined it. We defined that initial position to be 0, the launch position, and the peak velocity to be how far away that happens to be. So final answer is 328 meters.